So I wanted to go over the sample exam 1 that was given in class. So for problem 1, it's asking, it gives you, so it says, what are the units of the rate constant for the following rate equation? And then it gives you this equation, so RA is equal to KCA squared CB. So if you remember, the units for the rate are always some kind of amount, so moles per, say, liter, so some kind of amount per volume per time, so say in this case moles per liter per hour. And then the units of your rate constant K can change depending on what your other variables are in the rate equation. So the way you figure out the units for the rate constant are you just write down the units for everything else. So you have a concentration that's squared, so then say that's mole squared per a volume, so liters squared. And then you have another concentration that's not squared, so you have moles per liter. So then you can just start canceling things out and see what's left to figure out what K is. So first of all, you can divide out this mole. You can get rid of that. And so you can see that if you multiply over hours, then K, the units of K have to be liters squared, moles squared per hour. All right, so problem number 2, it says, what is the concentration of C in terms of conversion and other initial parameters for an elementary reversible gas phase reaction? And then it gives you a reaction. So I'm going to start writing some things down. So what I usually like to do with these problems is they sometimes give you a lot of information, and so I like to write down the information as I'm reading the problem, so then I just have it all there. And so first of all, this is the reaction. A plus 2B to 2C. And you know that it's elementary, reversible. You know it's gas phase. And then you also know that the feed has 1 mole of A and 2 moles of B, so feed 1 mole A, 2 moles B. So there were actually 2. So in the problem sheet in class that he gave, he asked for the concentration of C in terms of conversion and other initial parameters, but in the solution he gave the concentration of B, so I'll just do both. So what we want to find is the concentration of B in terms of conversion X, and then also the concentration of C. So the way you do these problems is you know all this information. You know it's gas phase, you know it's elementary. So you can go in chapter 3, there are several charts relating the concentrations to conversion. And so based on the information you're given, you just pick an equation off the chart. And I'm not saying that you shouldn't understand where the equation came from. It's important to understand where the equation came from, but for an exam and for assignments, you generally don't need to derive this equation every single time. So I would actually recommend making your own, like in your own notes, just write down all of these tables so that you have it and make sure that you understand how they're derived. So one chart that I found pretty useful in this book, this is Elements of Chemical Reaction Engineering by Fogler is this one. It's on page 112. And it has a reaction, and then it has, so if you have a liquid phase, you look down one column. If you have a gas phase, you look down the other. And so I felt like that was useful for helping to put all this information together, because it's a lot of equations to keep track of. So anyway, knowing what you know about this gas phase, and you can pick the right equation. And so for CB, you would have CB equals C A naught theta B minus B over AX over 1 plus epsilon X, and then P T naught over T. And one thing to keep in mind is if your pressure and temperature are constant, then these are both equal to 1. And I noticed in the solution that was given for this problem, he assumed they were 1 because they're just gone, so I'm just going to take those off. But I like to write down all the information, because then, so basically what you're doing is you have your equation, and then you're making some assumptions to simplify it so you can solve it. And so if you can assume that there's no pressure or temperature changes, then you can make the assumption that these are equal to 1. But I think it's good practice to write them down, because then in the future, when we start dealing with reactors that do have pressure and temperature changes, you're already used to writing them down, and I feel like it's just easier to keep track of information. So now we just need to solve the different parts in this. So we know that, first of all, theta B is equal to FB naught over FA naught. And so we get that from this because we were given the feed. So we know that FB naught is 2 and FA naught is 1. So theta B is 2 in this case. And we know that epsilon is equal to partial mole fraction multiplied by delta. And so Y A naught is equal to N A naught over N T naught, which is also equal to F A naught over F T naught. So in this case, once again, we can get this from here. So we know that F A naught is 1, and we know that the total moles is 3 because we have 1 mole of A coming in and 2 moles of B coming in. So the total moles are 3. And then we know that delta is, in this case, delta is C over A minus B over A minus 1. Yeah, you can still see that. And so in this case, and so these are the stoichiometric coefficients, so we know that, so this is C, B, and A is 1. So plugging these in, we know that C is 2 over A, which is 1, minus B, which is 2 over A, which is 1, minus 1. So this equals negative 1. So then we just go ahead and plug these things in. So we have this equation equals, so I'm going back to this one, C A naught minus theta B, which is 2, minus B over A, which, okay, so that's going back to this. So B over A equals B is 2, A is 1. So that's equal to 2x divided by 1 minus, and then we have this epsilon, which we have the YA naught is 1/3 multiplied by -1, so this equals -1/3. So then we have 1, and this was plus, so now it's 1 minus 0.333x. So this would be CB. And then for C of C, I'm going to go ahead and erase something so there's room. So for C of C, it's the same method. First of all, we would go to the chart in Chapter 3 and pull off the equation that you hopefully know how it was derived. And so in this case, it would be C of C equals C A naught theta C plus C over A x 1 plus epsilon x, and then that's multiplied by P over P naught, T naught over T. And so then we just do the same thing. We just figure out what these things are. So first of all, epsilon is the same, and so we just need to figure out theta C is equal to FC naught over FA naught. And we know that FC naught is 0 because there's no C flowing into the reactor, so this would just be 0 because you have 0 divided by 1, so that equals 0. And then we know that C over A is equal to 2 over 1. So then you do the same thing, just plug everything into this equation, and you have C of C. All right, so number 3 is actually number 4. So I'm doing number 3 in the solutions, and it's actually number 4 on the exam statement. So it says, write the rate of reaction in terms of concentration and components equilibrium constant Kc, and the rate of forward reaction K for an elementary liquid phase reversible reaction, and it gives you the reaction and the feed. So I'll just go ahead and write some of this down. So, and I'll write down, this is number 4. So we're looking for the rate in terms of concentration Kc, Ca naught, initial, and K. And this K is the forward reaction, so we know that it's elementary. We know it's liquid phase. And it's reversible. So the reaction is 3A plus B to 2C plus D, and then we have K and K minus. So K forward and then K reverse. And then we know that the feed is 3 moles A, 2 moles B. We know that Kc is equal to K forward over K reverse. And so it says to find the rate of reaction and then also show how the concentrations are related to conversion. So first of all, we'll find the rate and then find the concentrations. So for the rate, we need, since this is a reversible reaction, we need to do it in a couple steps. So first of all, we can write down the rate forward, and then we need to write down the rate in reverse. So since it says it's elementary, we know that the rate forward is equal to K CA cubed, because the stoichiometric coefficient for A is 3, CB, and it's 1 for that one. And the reason why we know that's 3 and that's 1 is because it tells us that it follows the elementary rate law. So then we can write this down in reverse. So RA reverse is equal to K minus, for this one, C squared C D. And once again, this is squared because the stoichiometric coefficient here is 2. This is just CD because the coefficient is 1 here. So then we know that the rate is RA is equal to RA forward plus RA reverse. So we can go ahead and plug that in. So RA forward was, and this is going to be negative because this, so it's just the the sign change. So this is showing the rate of disappearance, but this is, the way this is written, it's the rate of appearance, but it's negative, so, well, it's disappearing, so it has to be negative. So this would be K CA cubed CB plus this one, so C squared CD. And then we can multiply the entire thing by -1, because right now we have this is the rate of generation, but we want the rate of disappearance, or people call it different things, and so it can be confusing, but just try and keep track of the signs. So multiplying through by -1, we get the rate of disappearance of A is equal to K CA cubed CB minus K negative C squared CD. And then we want to pull K out. We want to pull this out, so rewrite this is equal to K C, and I mean technically this is the rate law, but there's well, first of all, it says in the problem statement that you need to write it using this in the equation, so you need to take this step, but there's just a certain way that these are normally written. So CA cubed CB, because we pulled the K out, and then we have minus K minus over K C squared C D, and then we know that is, we need to plug this in for that, so then we get RA equals K CA cubed CB minus C squared CD over KC. So this is the rate of the disappearance of A for this particular reaction. So then the problem says to find the concentrations in as functions of conversion. And you would need to do that in order to solve this equation, because you see that we have the rate and we have these concentrations in here, but we don't know what they are yet, so we need some equations for those. So I'm going to erase some of this. So this is the same thing as the last problem, only we have, this time it's liquid phase, and so we would look at the liquid phase table instead of the gas phase. And so just pulling these off out of the book, off the table, or you can also get them off this chart that I point out on page 112. But I highly stress just knowing where those come from, because you don't want to be randomly pulling these equations off tables and get the wrong one, because they're based on if you have gas or liquid, they're different. If you have, I mean they have different assumptions, so you might accidentally write down an equation that's making an assumption that you can't make. So just definitely make sure you know how those are derived and where they came from. So, and when I was first learning this, what I usually did was I made so if you look at the example problems in chapter 3, they usually have they'll often make a chart with, I'll show you an example. So for instance, on page 116, there's an example problem and they made a stoichiometric table for this reaction. So then they have a column with the species, a column with a symbol. They have initial, change, and then remaining. And then you could take this a step further and also have a column for concentration. And so when I was first learning this, I actually would make a table for the problem, because I felt like it was way less confusing than just writing down a bunch of equations. But for this exam review, I just want to write down the equations so that it's basically so you know if you're getting the right thing. But and on the exam, you probably don't want to make an entire table, because you might run out of time. But when you're doing your homework, I would make the table, or when you're preparing for the exam, I would make the table just so you kind of get a sense of where these things are coming from and how the equations relate to each other. So anyway, if we go look at the table for a liquid phase reaction, we know that Ca is equal to Ca naught 1 minus x. We know that Cb is equal to Ca naught theta b minus b over a x. We know that C of C is equal to Ca naught theta C plus C over A x, and we know that C of D is equal to Ca naught beta D plus D over A x. And another thing to keep in mind is all of these equations are written with A as your basis. So if you have a different basis, this will be slightly different. Like say your basis is B, everything would be divided by B instead of by A. So that's something to also keep in mind as you're doing these problems, and why you want to know where the equations on the table came from and not just rely on copying them down. So Anyway, now if we go through this, we need to figure out what theta B, theta C, and theta D are. We already know what A, B, and C are, so this is A, B is 1, this is C, and D is 1. So those are the stoichiometric coefficients. So for theta B, we know that theta B is F B naught over F A naught, and these were given right here. So we know that we have 2 moles of B and 3 moles of A in the feed. So this would be 2/3. And we know that theta C, so this is FC naught over FA naught. Since there's no FC in the feed, then this is 0. And the same thing for theta D, because there's no D in the feed. Whatever chemical D is, it's not in the feed. And so then the last part is just so B over A for this is equal to, you just look at B, 1, A is 3, so that's 1/3. C over A, look at C, is 2, A is 3, so that's 2/3. And then for D over A, this D is 1, A is 3, so that's 1/3. So then you would just plug these in to get the concentrations in as a function of conversion. So number 5 says the first order gas phase reaction, so you can write that down. So we know the reaction is A to 3B. We know it's first order. We know it's gas phase. And the initial pressure, which is constituted with 50% A and the rest inerts, is 2 atmosphere. So we know that P naught is 2 atmosphere and it's 50% A and 50% inerts. It says if the rate constant for the reaction is 0.05, so K equals 0.05 per minute, how much time would be needed to reach a pressure of 3 atmospheres in the reactor? So what we're looking for is the time to reach P equals 3 atmospheres. I'm going to also assume that this is isothermal and it's a constant volume batch reactor. So in order to solve this problem, we need to first calculate the conversion in the reactor when it reaches 3 atmospheres, and then you can take that conversion and put it in the design equation for a batch reactor and calculate the time required to reach that conversion. So first of all, we need to use an equation that you can relate the initial pressure and the final pressure to get the conversion. And so we're going to use the equation for, so it's the equation for a variable volume batch reactor. It's on page 110. So I'm going to write that down. V equals V naught P naught over P 1 plus epsilon x T over T naught. So looking at this equation, first of all, if we assume isothermal, this is equal to 1. And then we also know that it's constant volume, so V over V naught is also equal to 1. So V over V naught equals 1. And so we're left with P over P naught is equal to 1 plus epsilon x. And so then we can just figure out what these are. So we already know the final pressure, we know P naught. So we need to figure out what epsilon is so we can solve for x. So epsilon is equal to YA naught delta. And so this is the partial mole fraction. So we already know that YA naught is 0.5 because A is, there's 50% A in the feed, so this is equal to 0.5. And then we know that delta is equal to C over A minus 1. So C, actually this is B, sorry. So B is 3, A is 1, so this is 3 over 1 minus 1, which equals 2. So then we know that epsilon is equal to YA naught, which is, oh, I'll just write it up there. So delta, we can just plug in the 2, so that equals 1. So then we can go ahead and plug that in into this equation. So we have P over P naught is equal to 1 plus x. So then plugging in P, so the P final that it gave us is 3 atmosphere. So we have 3 over 2 is equal to 1 plus x. And then if we solve that for x, we get that x is equal to 0.5. So when the basically when the reactor reaches 3 atmospheres, then the conversion is at 50% of A. So then we need to find so then the next part of the problem is to find the time required to reach that 3 atmospheres and the 50% conversion. So I'm going to erase some stuff. Actually, I'll write down x. So we calculated that x is equal to 0.5. So in order to get the time, we need the design equation for a batch reactor, which is in Chapter 2. So writing that down, we know that the time is equal to NA naught over, skipping ahead. So we know that it's equal to the moles multiplied by the integral of 0 to x dx over minus r AV. And since it told us this is first order, we know what the reaction rate is. We know that it's RA equals KCA. And then we know that this is, if we write this in terms of conversion, we know that this is equal to K CA naught 1 minus x. So if we plug this into this equation, we get T equals NA naught over, and first of all we can pull this V out because it told us this is constant volume. So this is V, and then once we plug this in, we also know that the K and the CA naught are constant, so we can pull those out too. So we have K, CA naught integral 0 to x dx 1 minus x. And then this is moles over volume, so we know that this is concentration, so that's CA naught. So then we can cancel these out, so we're left with T equals 1 over K 0 to x dx 1 minus x. And so then we can go ahead and integrate this, and there are some integration tables in the back of your book for these common ones, so if you don't remember what it is, just you can look it up in the book. You can also look at Wolfram alpha or whatever. So solving this, we know that T equals 1 over K natural log 1 over 1 minus x. So then we should know everything we need for time. We know what K is because it was given. We know x because we solved for it in the previous part. So if we plug that in, we have 1 over K, which is 0.05 minute minus 1, natural log 1 over 1 minus 0.5. And solving that, we get 13.86 minutes to reach 3 atmosphere and 50% conversion in the reactor. So for this problem, I wrote down I drew the graph already just to save time. So the problem statement says inverse of the rate versus conversion. So this is inverse of the rate versus conversion for a second order reaction. So I'll write that down. Is shown in the following figure. Units of the rate are moles per liter hour, so rate moles per liter hour. Pure A is fed to the reactor at a volumetric rate of 1,000 liters per hour, so volumetric flow rate is equal to 1,000 moles per liter. And then it says a 500 liter CSTR is available for the reaction and the conversion desired is 0.8. What is the conversion with the 500 liter CSTR? If you decide to place a PFR in series downstream with the CSTR to achieve the desired conversion, what is the required PFR? So we know that we want x equals 0.8 for the conversion. And we know that we have a 500 liter CSTR available. And let's see, is there anything else? Oh yeah, so also we know that the concentration, so it says that the concentration of the feed has a concentration of 0.005 moles per liter, so CA naught is equal to 0.005 moles per liter. And then it wants to know what is the conversion for the 500 liter CSTR, and then if we want to have a conversion of 0.8, what PFR volume do we need to put in front of the CSTR to reach that? Because it says, actually, sorry, downstream. So we would end up with something like this. So we have a CSTR that's 500 liter. And then we have a PFR, and we need to find the volume. So, and we want that, and we need to find out what this is, and then that volume. So first of all, we can also calculate the molar flow rate because we have the concentration and the volumetric flow rate. So we know that FA naught is equal to volumetric flow rate multiplied by the concentration. And this is 1,000 liters per hour multiplied by 0.005 moles per liter. So then this equals 5 moles per hour. And then if we look at the design equation for a CSTR, we know that this, so we get this equation. So the volume is FA naught over minus RA multiplied by X. So then if we look at this, if we rearrange this equation a little bit, so if we divide FA naught over, then we get V over FA naught equals 1 over the rate multiplied by X. So if we just look at this equation, we know that we know everything for V. We know the volume. We know the molar flow rate, so we can calculate this. So V over FA naught is equal to, we know it's 500 liter, and we know that FA naught is 5 moles per liter. So then calculating this, we get 100. So then if you look at this, we know that we have 1 over the rate multiplied by the concentration, and this is just an area. So we know that when we multiply, we know that the area for the CSTR has to equal 100. So what we do is look at this graph and figure out where on the line it equals 100. So for instance, if we multiply 0.2 by 200, that doesn't equal 100, so we know it has to be further up. If you go to the 0.6 multiplied by 400, that's more than 100, so you know it has to be lower. So the answer is actually 0.4 multiplied by 250 is 100. So then you know that your conversion for this particular CSTR is 0.4. So we know that this x1 is 0.4. So then the next part of the problem, so we want a conversion of 0.8, and so what we're going to do is put a plug flow reactor, a PFR, after the CSTR in order to get the 0.8 conversion. So I'm going to erase some of this stuff. So the way you do this from the graph is we know that we want 0.8, and if you remember for a PFR, the volume, so we want to add up, we want to calculate the volume under the curve, so basically this. So you can calculate that volume however you want, and the way I did it was I just calculated this area, and then I calculated this divided by 2 and this divided by 2. So I just calculated this, and then I added this and this to it. And when I did that, I came up with 185. So so 185 is the area under this. So if you look at the design equation for a PFR, then, so this is the design equation for a PFR. The volume is volumetric flow rate, or sorry, the molar flow rate, 0 to x, dx over minus RA. And so this is the volume. So from this plot, we already know that this is equal to 185. And so we should just be able to multiply this by the molar flow rate to get the volume. So then if you do that, the volume, so this is 5 moles per hour multiplied by 185, and probably should have kept track of the units of that, but this is equal to 925 liters. So for the last problem, it says this is number 6. It says the conversion of an irreversible first order liquid phase reaction taking place in a CSTR of 300 liter capacity is 60%. In order to increase conversion, the engineer installs a 100 liter PFR upstream of the CSTR. What is the exit conversion in the system? So we can go ahead and write everything down. So we know that, first of all, we know that it's irreversible. We know it's first order. We know it's liquid phase. We know that we have a CSTR that has a, let's see what it say, that has a volume of 300 liters, and that it's capable of its conversion is 60% or 0.6. And so I think for this problem, it helps to draw a picture of what you're actually solving, because you have two reactors in series. So first of all, it says that you have a CSTR that's 300 liter. And then it says that you install a PFR upstream, so that's in front of it. That's, think of the size of that one. Yeah, so you know this one's 100 liters. And so you have some flow, you have whatever you're reacting flow in. You have a certain conversion from the PFR, and then you have the total conversion from the CSTR. So I'm gonna, at this point, if I was going through this problem, I would write down the design equations for a PFTR, or for the PFR and the CSTR. So for the PFR, it is V equals FA naught integral X in, X out, dx over the rate. And for a CSTR, it's FA naught X out minus X in over the rate. So the first thing we need to do is, so we have this PFR and we need to find out what X out is, so then we need that to solve this equation. So first of all, I'm going to solve this equation. So So first of all, I want to write down the relation for the concentration and the molar flow rate. So Fj is equal to the concentration times multiplied by the volumetric flow rate. So then if I plug that into this equation, then I have V equals Ca naught times the volumetric flow rate multiplied by the integral of x in, x out, dx over the rate. And so then I can, and then we also know that the rate is, so it tells us that the rate is first order, so I'm just going to say that the rate is K Ca, so then that equals K Ca naught 1 minus x. And in this case, that okay. So then I can go ahead and plug that in too. So then I have V Ca naught V naught dx over K Ca naught 1 minus x, x in, x out. So then I can pull these two things out because they're constant, and the Ca naught will cancel out. And I can also divide, I'm going to divide the V naught over, and then this becomes the space-time constant, which is written as tau. And so then this equals 1 over K x in, x out, dx over 1 minus x. So then I can go ahead and integrate this. First of all, I know that x in is equal to 0 because there hasn't been any conversion yet. And so integrating this, I get that tau is equal to 1 over K multiplied by the natural log of 1 over 1 minus x. And I'm going to change, so I've been calling this x out. I'm going to actually call it x1 because that's what I've written on the picture. So this would be x1 here. And let's see. So I know that changing this again a little bit, I'm going to multiply through by k. I'm going to switch tau back to V over V naught. And then this is equal to the natural log of 1 over 1 minus x1. And so we need to solve for x. We want to solve for x1. We know the volume, but we don't necessarily know those. So to get these, we want to solve the known CSTR equation, because it's already told us that if we're just using the CSTR by itself, then we get a conversion of 60%. So we should be able to solve the CSTR equation and figure out what K over V naught is. So I'm going to go ahead and do that. Let's see. So I'm going to have to erase these equations. So using the design equation for a CSTR, we know that V is equal to FA naught X out minus X in, which is 0 in this case because so basically we're taking a step back and we're assuming we only have a CSTR and we know the conversion and we want to solve it to get this K over V naught, so then we can solve this equation. So this is K CA naught 1 minus X. And yeah, because so this is divided by the rate, and so I just plugged in the rate directly. And so then using this relation, I can go ahead and put in the C A naught V naught multiplied by X out over K CA naught 1 minus X, so CA naught cancels, and then you can see that we have this V naught over K right here, and we know everything else, so we should be able to solve this to get the V naught over K. So we know that, well, let's also rewrite this. So I'm going to multiply over the K, divide through by V naught, and this equals so this equals X out divided by 1 minus X out. So then we know the volume. We know it's 300 liters. We know that this is 0.6. So then we can solve for this. So doing that, we know that K over V naught is equal to 0.005. So then we can go ahead and plug that into here. And then we should know everything to solve what x1 is out of the PFR. So we plug in 0.005 for this. We know the volume is 100, and so then solving this, we get the x1 is equal to 0.39. So then I can write that down. And then for the second part of the problem, we need to solve what the conversion is for the CSTR when it's in series with the PFR. So I'm going to erase this. All right, so for the CSTR, we want to go back to the design equation again. And I'm just going to copy this down rather than writing it from scratch. So the design equation for the CSTR is the V CA naught V naught. Oh, actually the CA naught cancels out. So V naught over k, and then x out minus, and then in this case this isn't 0 because we already have some conversion from the PFR when it's coming into the CSTR, so in this case that would be x1, I'm going to change this to x2, divided by 1 minus x2. So then I can multiply, so I can multiply the k over, divide by volumetric flow rate, and then that equals x2 minus x1 over 1 minus x2. So then I can plug everything in. I know that the volume is 300. I know that k over v naught is 0.005. And I know x1, so x2 minus 0.39 divided by 1 minus x2. And then if you solve this equation for x2, you get that x2 is 0.76. So the total conversion for this is 0.76.